Hey kiddos, and welcome back. I'm so thankful for your tenacity in working through this conversation about atomic structure. We're finally moving into atomic structure. Again, primarily a review, but digging a little bit deeper to understand it better conceptually. Now, what our goal is to locate an electron somewhere near the nucleus. I fondly like to call this the electron playground. Now, in order to describe the location of an object, we typically need 3 coordinates. Our goal is to have an internal coordinate system relative to, that's an L, sorry, relative to the nucleus. Now, we are fortunate we get a bonus 4th that helps us understand the structure and property of atoms and electrons even better. Some of the contributing factors to this, to building up to the quantum model, Bohr. I know I don't like the Bohr model per se in the orbiting electron issue, but he did provide us with that idea of quantized energy levels. Quantized means that not all energy levels are allowed. So it's more like steps, not like a ramp. That's what quantized means. Max Planck helped us out by providing the wave nature, the particle nature of a wave, in that energy is equal to h nu. Remember, h is Planck's constant. Now, there's a twin concept that de Broglie came up with. If there's a particle nature of waves, de Broglie said, well, what about a wave-like motion for a particle? And this is all I'm going to talk about. It's called the de Broglie wavelength. I just want you to see that mathematical application, particle-wave duality, goes back and forth. Heisenberg and Born helped us out by coming up with the uncertainty principle. In other words, the best we're going to be able to do is define a playground where the electron is most likely playing with a given energy. And that's called the uncertainty principle. And sorry about that, my computer's yelling at me right now. All right, what that means is that it is impossible to simultaneously know the position and the velocity, that's momentum, P, mass times velocity is momentum. It's impossible to know both of them exactly. So there'll be a certain change or uncertainty in the position, and there's going to be some uncertainty in the velocity, and it's always got to be greater than Planck's constant over 4 pi. It's amazing how pi just shows up everywhere. So the more uncertain we are about the position, actually the greater we can know about the velocity, and vice versa. And that leads us into the fact that we're only going to be talking about the probability of finding an electron. And there's all sorts of fun Heisenberg jokes online. So you're tasked with finding some fun, school-appropriate Heisenberg jokes and Heisenberg uncertainty principle online. So let's take a look at some of the foundations for this. This leads us into Schrodinger's equation. Actually not too bad to solve for the hydrogen atom. Very difficult as we get into many electron systems, but not too bad for hydrogen. And the solutions are called wave functions because we're using the mathematics of waves to come up with a mathematical function that will help us understand the energy and location of an electron. And it's a triple integral for those of you who are in calculus. Those are partial derivatives, and I used to be able to solve it, but I have no idea how to do that anymore. We're only going to look at the solutions. A wave function is given the Greek letter psi. Wave functions are quantized. Only certain ones are allowed. Okay, and it solves for the energy exactly, but only gives us a probability about the position. Energy is related to velocity. That goes back to Heisenberg's uncertainty. The square of that gives us a function that will describe a 90% probability of finding an electron with a specified energy. And that's what we're going to be exploring. And the way we model that and explore that. So the coordinates, those internal coordinates that we talked about, can help us describe this. And these were the 4 coordinates. You saw them in pre-AP. We're going to buzz through them very, very quickly. We have the principal quantum number n, angular momentum quantum number designated by L instead of using XYZ. For unknowns, we're using NL M sub L because M sub L is related to L. And then the spin quantum number M sub S. And this is such an important concept here. The region in space where there's a 90% probability of finding an electron with a given energy is such that electron-electron repulsion is minimized and electron-proton attraction is maximized. It's all going back to, you got it, Coulomb's law. All right. I've got a new little inking program here, and it's taken me a little while to get used to it, but hopefully you're going to be patient with your teacher. All right, let's run through these because there's not much difference in these that we had in pre-AP chemistry. So our energy levels, sometimes called an energy shell, so you've got to be able to use those terms interchangeably. Bohr really helped out with this, and Schrodinger's equation really reinforced it and brought it into better, calculated form, quantitative form. Now, energy levels are described by, remember we call this a quantum number, the quantum number given the symbol n. Now, the number of electrons in each quantum number is given by this formula. Now, n can't be 0. That will be illogical, as you're going to see in a minute. N can't be 0. It takes on all integer values, 1, 2, 3, 4, 5, 6, and so on. And if you wanted to know the number of electrons in an energy level, you could use this formula. So if we're talking about energy level 3, we have 2 times 3 squared. 3 squared is 9 times 2. That means that energy level 3 can hold up to 18 electrons before electron-electron repulsion gets to be too high, and you just can't fit in anymore. Now, there's 2 key pieces of information it provides. It not only gives us primarily most of the energy information about the energy, but it also tells us distance from the nucleus. As energy level increases, the distance from the nucleus also increases. So you have a nucleus here, and if you had an electron here, an electron here, this one is closer, okay? Its energy is more negative, right? Because we're talking about attractive, and those are more negative and closer to the nucleus. Now, to calculate this, we can use this formula. It's pretty good for hydrogen. It gives us an approximation for multi-electron systems, and I'm going to show you some calculations with this in a later video. All right, and I already mentioned this. Each energy level can hold up to 2n squared electrons. Okay. Now I'm going to see if I can buzz through these and still have a reasonably length video for you here. So let me get into some terms before we actually look at some energy level diagrams. All right, so that's where we're headed. I want to talk about these terms first, and then we'll move into the diagrams. Great flash animation for this. Now, the key terms that we have here are, all right, ground state. Whenever we do, and I'll refresh your memory on how to do an electron configuration, we're laying out the ground state. This is when attractive forces are maximized and repulsive forces are minimized. And the atom at that point will have the lowest potential energy possible. And that's going to make it very stable. Low potential energy is very stable. An excited state is when an electron, so if this is my nucleus, and again, let's get a different color, and here's my electron. When, let's say the electron likes to be here, an excited state is when we're somehow going to be able to free that electron up to move further away from the nucleus. So in an excited state electron, in an excited state for an atom, one or more electrons move, energy is absorbed in the form of heat, electromagnetic radiation. This is what's occurring in the fluorescent lights, by the way. They go from lower to a higher energy state. So for example, going from n equals 2 to n equals 5. Takes more energy. It's an excited state. The potential energy is less negative, it's higher, and it's less stable. And electrons don't stay in that excited state for very long. My analogy for an excited state is, my ground state is at home on my rocker, typically reading the paper with a cat in my lap. And let's say the phone rang. And if the phone rang and it was Denzel Washington, you can bet I'm going to move away from my ground state. And I'm going to be very, very excited. And I'm going to be moving. And it's going to be a thrilling, not very stable state for me. All right. Now, when electrons are at a less stable state, they're not going to want to be there for very long, and they will relax. During relaxation, they emit energy going from higher, so for example, n equal 5, to a lower state. So in my example, I very quickly realize, or at least Denzel quickly realizes he has the wrong number, and he hangs up, and I relax. Now, in my case, I'm going to call my sisters, I'm going to call my husband, I'm going to be so thrilled. But, hey, eventually that is going to wear off. Quit yelling at me, computer. And I'm going to relax. Now, when electrons relax, all right, they give off electromagnetic radiation, H nu. All right, and that's what we're going to be evaluating in our next series of videos. So until then, this is signing off.